In this lecture, we're going to be talking about linear quadratic regulators. So in previous lectures, we developed a successive loop closure technique for designing our control law. But we also, and those utilize the transfer function models. But in chapter 5, we also developed these state space models. And so we're going to utilize these state space models directly in LQR. So in this lecture, we're going to review the state space model generation, just what did it mean. And we also, in our developing the controllers for the successive loop closure, we looked at integrals. We added integrals. And so we're going to step in and talk about, well, how would you add integrals into our state space model? And then finally, we'll look at an LQR formulation, just general, and then we'll briefly go over how you might apply LQR to both the lateral and longitudinal dynamics. So let's go ahead and get started. If you recall our state space modeling, what we did was we had our dynamics. We've seen this function several times. We had dynamics f of x u, right? And we linearized, and we took some time doing this. We linearized about an operating point. And we called this x star and u star. And we defined the deviations. We said that our x was then going to be equal to our nominal state plus some deviation. And similarly, we did the same thing for u. So we said that u was equal to our nominal input plus some deviation. And we're assuming that these deviations are going to be somewhat small. So we found a model. We said that our x bar dot was equal to a x bar plus b u bar, where a was equal to the partial derivative of our dynamics with respect to x evaluated at the nominal values, and b was equal to the partial derivative of the dynamics with respect to u, again evaluated at the nominal values. Okay. So we have these x bar terms, and again, we can do this assuming that x bar is small. And we never have defined what that means, but it actually works quite well for decent deviations. So it's really wherever this linear portion of our system is dominant. And keep in mind that we want to send x bar to 0. So we have this deviation, and we want to get rid of that deviation. So that's our control is helping to keep things small. This lecture has, for the notation, instead of using x bar, it just uses the x dot is equal to ax plus bu, i.e. it should use x bar dot and x bar and u bar, but just keep in mind that we're going to just develop things for a general state space formulation, and this is really the general model. X dot is equal to ax plus bu. But keep in mind that we're going to send x to 0. So it's really the same thing. We just drop the bar. We drop the bar. So, okay, so when we designed our controllers, on our outer loop for the sequential loop control design, we had integrals to help us get rid of steady state error. So we need to be able to define integrals for our state space system as well. So we have x dot is equal to ax plus bu. That's what we wrote on the previous slide. We have our desired values that we care about and the ones that we're going to have our integrals on. We're going to define as z is equal to hx. Now, we're going to simplify things just a little bit here because on the next slides they're actually already simplified. So we have a reference signal. We'll just assume we've defined things such that we want to send z to 0 as well. Otherwise, the notation on the next slides doesn't actually quite make sense. So we've done a change of state, and just like we did up here where we were sending x bar to 0, right? We're going to do the same thing. We're just going to assume that we're sending our error to 0. So z is just really our error state. Okay, and that eliminates this component of that. So that'll help us write up our model here on the next slide. Now, one thing to note, we're going to define this integral state. So x sub I, this is our integral state. Well, if we take the time derivative of that integral state, it's just going to be equal to z, which is equal to h times x. So we're still defining our dynamics in terms of x, which is pretty cool. Okay, so if we come into look at our state space integral control, we're going to define this augmented state. Okay, so we're going to do our augmented state. We'll call it C, right? And so we have we're going to form augmented dynamics. So we're going to define this augmented state with its dynamics. And sorry, I'm slipping up here. Our augmented state is just going to be x and xi. So if we were to write that out in our standard notation, we just have x or column format, x and xi. Then if we took the time derivative of this guy, it's going to be x dot and xi dot, which is equal to ax and hx, which is where we get, plus, we'll sneak it in there, bu and 0. So this is where we get this term, this block matrix A and the block matrix B. Because everything only depends on x, there's no dependence on this variable xi. And so that's where we get, there's zeros, is there's no dependence on xi in the dynamics. Okay. And also this 0 is that our xi dot does not depend on any input. Okay, so what we want to do is our goal is we're going to define our u is equal to minus k times c, such that the eigenvalues for this closed loop system, and would represent the eigenvalues as a minus, or the closed loop system is going to be a minus b times k. And we want those to be in the left half plane. Because if we do that, oops, that should have been bar. If we do that, then we're going to have our system converge to 0, which if we've designed our system such like here, where we have our x bar, we're trying to send it to 0, that's the goal. Okay, so we have that is our goal. But then our question that we need to answer is, how do we choose? Okay. All right, so let's just review just a tiny bit. The state space integral control, all we're doing here in these two slides are saying, hey, there may be terms that we want to take an integral of. For example, in the previous lectures on successive loop closure, we designed integrals on, for example, the error in our coarse angle. So there are states where we're going to want an integral so that we can cancel out any steady state error. So these two slides are just saying, hey, we can define integrals just fine in state space, and it's fairly simple. Now that we have our full augmented dynamics, the question is, how do we choose that feedback gain matrix K? All right, so to do so, we're going to we're going to use LQR. So it's linear quadratic regulator theory. And again, now we're abusing notation again. In the previous slide, we could have been or should be using here this A bar C plus B bar U, right? But we're just going to define LQR general for just a general system that has dynamics x dot is equal to AX plus BU. Okay, so the linear portion is that we have linear dynamics. So we have a linear dynamics. The quadratic portion is that we end up having a quadratic cost. So these two terms are quadratic. And the regulator is that we're sending to 0. Okay, so we've just redesigned our dynamic state definition so that we're wanting to converge to 0. And we'll then converge to our nominal. Okay, so to give you a little bit more intuition on this quadratic cost, let's do an example. Okay. Let's let x equal to x1 through x2 and x3. If our costs were defined as q1 x1 squared plus q2 x2 squared plus q3 x3 squared, then this is equivalent to x transpose times q1, q2, and q3, put zeros everywhere else, times x. So that's our matrix Q that we're showing right there. So that's how we define our quadratic cost. Now what this, and maybe I'll be more explicit, right here we have zeros. Oops. Right? If we want, we could define cross terms right here. So that we'd have Q1, 2, and we'd have to keep things symmetric so we could define a Q1, 2 down there. So this would allow us to have, we'd have Q1, 2 times our X1, X2. Okay, so the one thing that we have to do is we have to keep it positive semi-definite. So it needs to be symmetric, and the eigenvalues of the matrix have to be reals and either 0 or positive. So we do have some limitations on what we can do, but if we just do positive values on the diagonal, then we'll be good. Okay, so we're going to minimize this quadratic cost, and the amazing, miraculous thing that happens is if we minimize this quadratic cost and our system is controllable, and we have this observability term where this is just satisfied if Q is diagonal with positive elements, then that's trivially satisfied. Then we have a unique optimal control, and the cool thing about that, even though we have this infinite time cost, or it's actually because we have the infinite time cost, we end up getting this constant feedback matrix. So really cool. So takeaway, linear, we've defined our dynamics already as linear. Quadratic, we define this quadratic cost with some conditions, and we're going to say that R is positive definite and Q is positive semi-definite. We are controllable and we're observable, then we have this feedback control that we can use for controlling our system. So the Feedback control is given by this K is equal to R inverse, where R again is defined right here, right? So in our cost. B is from our dynamics, where our input comes into play. And P is a solution, is a symmetric positive definite solution to what's known as the algebraic Riccati equation. And so in any controls toolbox, they'll typically have something that helps you either to solve the ARE or to solve the, just give you the LQR, the feedback matrix directly. So for example, in MATLAB, we have that K equal LQR, and we just give it the A, B, and Q and R matrices. Okay, so we can design this control. So the steps to do it, there's one, we have to define A and B. And this we used our augmented state from before with our integrals, right? And we called it A bar and B bar, but that's fine. It's just our system matrices A and B. The second thing we need to do is we need to define Q and R. And when we're defining our system matrices, we better be completely controllable. When we're defining these cost matrices, we have conditions where R must be positive definite and Q, if we just let it be positive definite, then we're good. But we have a positive semi-definite and an observable condition. Okay. Our third step is that we solve the algebraic Riccati equation for a positive definite value for P. And then fourth, we're going to calculate, calculate with a C, our K, L, Q, R. So we have now this ability to do LQR control given just any generic A, B, as long as some conditions are satisfied. And the next slide just talks just a little bit more about it. Just to note that K is the optimal feedback control given by the definition of Q and R. Typically, we define Q and R to just be these diagonal matrices, right? And if we allow, we must have that, if we define it with these positive or with diagonal elements, must have that the elements of R along the diagonal are greater than 0, and the elements of Q along the diagonal are greater than or equal to 0. And if we again if we just force that Qi is greater than 0, that will imply that our observability condition is met. It's sufficient, but it isn't necessary. Okay, so we have our LQR all wrapped up, right? And we have an entire course where we really give all the background on the LQR. Okay, so now let's talk about the lateral component of our autopilot. So we again, in chapter 5, we separated our state space models into a lateral and a longitudinal component. We have our lateral states that we're using and our lateral controls that we're using. We're going to add in just an integral on our course angle. And yeah, and then we're pretty good to go. So if we just approximate this, if we make this approximation, then it's a simple linear relationship. Okay, so that defines, again, we get our, right, the A and B matrices. So it's going to be with this, it's going to be combination of, well, not that guy, H and that A lateral. Okay, and then we come down here and we have our augmented state matrix like we mentioned before. We define our Q and R as these are the cost values, and these are really our new control knobs, right? So if these now become our new control knobs. And then we use the ARE to compute our feedback matrix K. Excellent. So that would be just a basic overview of the lateral autopilot. The longitudinal, again, we have very similar thing, except for now we've designed our longitudinal states. In this case, we have two integrals. So we have our H value defined like that. So that gives us our integral. So again, to get our A matrix, we combine those two using our augmented state, right? So this is what we were talking about on the previous slide. And then again, we have our new control knobs, and we use the ARE to come up with our KLQR. So now we can design the LQR control there. So that's just a basic overview of how we would use LQR instead of the successive loop closure technique.